Hello everyone. Let's begin. So, okay, yep. Today in 201, basically what we're going to talk about is asymptotic analysis. Okay, from the perspective of computer science. So the question is, of course, what is that? And the answer is basically, it's the study of how long our algorithms take when we change the input size, and most notably when our input size heads off to infinity. Right, so the idea here is that the goal is to understand in general which algorithms perform best and which ones don't, and it's to understand relatively how long things will take. So let's begin by discussing the two types of searches that you can generally do. So there's a linear search, and then there's a binary search, which we haven't talked about yet, but we'll talk about both of them now. So what is a linear search? So if you have a list, right, so you have some list, so take any list, and what we're going to do is look for an element in that list, okay? So assuming that the element is, say, x, right? What we're going to do is we are going to go and say for lm send in the list, right? And then we'll do something like if x is equal to the element, then we can, if this is in some kind of function, we can return true, or if it's some boolean, we can say found equals true, right? So that's a linear search, right? So basically what this does is it just looks through every element in the list one by one. And okay, that's fine, right? There's nothing wrong with that. It's definitely one way to search through elements. So let's talk about a binary search, right? So what is a binary search? So the one requirement for a binary search is that we require that the list be pre-sorted. Okay, so you might say that that's a huge requirement, and it is. And in general, if your list is not pre-sorted, then the best you can do is generally some kind of linear search. But let's say that the list is already sorted. So for instance, if our list is already like 1, 2, 3, 6, 8, 13, 25, and I tell you to say look for the element, let's look for 13, okay? So how are we going to do this? Well, if normally what you would do is something like, well, I'll compare, if we're going to do a linear search, we would say, is 1 equal to 13? No. Is 2 equal to 13? No. 3, 6, 8. Finally, you get to 13 and you'd say yes, and you'd return true. Or, so you could scan through and eventually return true. And if you say look for the element 7, you scan through and you get to the end of the list and you don't find it, and so you return false. Okay, but now let's talk about if there's a way to improve this, right? So this is still linear searching, so is there a way to improve it using the fact that there are, well, let's count the number of elements in this list. There's 1, 2, 3, 4, 5, 6, 7. There's 7 elements in the list. So what if I look at the 7 divided by 2th element, right? Which is, we would call that element 3, right? 7 divided by 2 is 3. And so we would look at the 3rd element, and so we say, okay, the 0, 1, 2, and so the element here is, and say we're looking for 13. So go back to searching or 13. So what we're going to do is we're going to look at the middle element, right? And so when we look at the middle element, we're going to say 6, right? And then what do you know? The only thing that we really know about this list is, so we say the list at 3 is equal to 6, right? So that's true. And we know the list is sorted, right? So we know these two facts. So I guess the only question we have left is it possible that 13 is in this lower half here, right? Is it possible that 13 is under 6? And the answer is, assume that the list is sorted in ascending order, right? Not descending order or something. I'm not trying to trick anybody. So if we assume that the list is sorted in ascending order, and we know that the element 6 is right in the middle, and we're looking for 13, then it's not possible, right? There's no way that the, totally not possible, right? Right? 13 is less than 6 is false, so no, right? So that's the thing. Everything on this side has to be less than or equal to 6. Everything over here has to be greater than or equal to 6, right? The list could be entirely made of 6s, but in this case, it's not. So, okay, so now what we do is we say, okay, let's look at the remaining part of the list. So now we look at just this part here, and what we're going to do is we're going to look at the middle element again, right? So now look at the middle element again. And of course here you'd say, well, what's the middle element here? The middle element here is, it's actually the list 0, 1, 2, 3, 4, 5, so it's the list 5, but, so the list 5 is the middle element, whatever that means, right? And so then what do? Then you say to yourself, okay, let's look at the list 5. The list 5 is equal to 13, return true, right? Cool. So what do we notice about this process? So notice the important thing about this process. If you start out with a list of size n, right, then what happens? What's the next? You see that we're going to divide the list in half. We're going to look at the middle element, and approximately, so I'm not looking for an exact number, so approximately how many elements are in the remaining list if we don't find the thing? So the answer is going to be n double divide 2, right? So this is the Python round down thing. So, so if the middle element isn't the thing, yeah, exactly. So it's n over 2 is the second size of the list, right? And then we divide it in 2 again. So the first size was 7. The second one was 3. The third one was, I guess, 3 divided by that is 1. So if we were looking at either 8 or 25, and then it would be down to 0. So what's going to happen if we divide the list in half? Again, right? So it would be n divided by 4, right? So if we had to search a third time, n divided by 8, search a fourth time, all the way down. And so finally what we're going to end up with is something where n divided by something is approximately equal to, well, I'll just do, is approximately 1 or 0 or somewhere in there, right? Basically like something like this. 0 is less than this is less than 1. Eventually this will be the case, right? So the question is, what is that something, right? So the first thing we should do, let's actually write the binary search algorithm, and then we'll come back to this analysis, right? And so let's write the binary search. Let's see, where is my Python? I have lost you, Python. Here you are. So I'm not sure how much coding we'll do today, so maybe we'll do some coding. Actually, let's just keep it inside of the sorting because, okay. So this is not really a sort. There we go. So to do any kind of search, we need a list and some element, right? And so what we're going to do is we're going to say for x in a list if x is equal to element, return true, and then at the end, return false. So that's our linear search, pretty easy to code up. So for our binary search, we need a list, we need an element, and we might need some extra stuff, or I might make a helper function. Maybe I'll make a helper function just to do an example of making helper functions. So I'm going to make a helper function called binary search recursive. And I'm going to have it with a start and an end. And you might kind of be able to guess where I'm about to go with this, but the first thing we're going to do is we're just going to return binary search recursive on a list element. And then what's our start? Well, we haven't done any searching yet, so our start should be 0. And the last thing that we want to search is going to be the length of a list. Whoops. So now you can kind of see what I'm going to do with the start and the end, because basically, why do I need the start and the end? And you can see it right here, right? If I'm going to search the whole list, I want from 0 to element 7 to be the whole list, and then when I'm just searching here, I want it to somehow know that I want to do the element 4 up to the element 6, but really we might end up putting 7 in here. But the point is that we want to be able to tell it where to start and where to end, because the place to search, right, is really equal to start plus end divided by 2, right? That's where we're going to search. It's the formula. So this is the midpoint formula, right? So in the binary search, what we're going to do is say if a list at place to search is equal to, and we'll have to deal with some kind of boundary cases in just a second, but let's just do this. If it's equal, we're going to return true, not false, like I was about to type. Elif, the place to search is, let's say, if element is less than the thing at the current position, then what we're going to do is we're going to return binary search recursive on a list element. Those always stay the same. But now we know that we have to start where we started, right? The start is the same, but the end is the place to search, because the end is the midpoint. Okay? So what that means is that we want to, basically what we want to do is we want to start at the initial position, but only go up to the midpoint, right? Because we know that the element is before this position. And then finally here, else, we can return binary search recursive, and you can maybe even do place to search plus 1, because we know it's not there, up to the end, like this, right? So this just bypasses the place to search. This is not technically necessary. You could just still do it like this and it would work just fine. I'm just doing it like that anyway. Okay, so and then, so we need one more thing here. So what if the end is less than the start? And so how can that happen? What can happen here is that if we never find the element, adding 1 to this place to search might actually, if place to search is equal to end, if start is equal to end, then place to search is equal to start and end, right? They're all equal to each other. And so in our next step, we would be adding 1 to the place to search, which would put the start after the end. So then end would be less than start. And so what happens in that case, what that means is that we failed to find the thing, right? So if end is, I think actually if end is less than or equal to start, we can return false. Okay? And what this basically means here is that if end is less than or equal to start, and of course we should test this function, but if end is less than or equal to start, what that means is that this thing has taken over, or we've gotten down to a single element and we just haven't found whatever it is. So, okay. The other way to do it, there's another way to do this with slices, so let's implement this with slices. Maybe you'll like slices better. Because slices means you won't have to do any of this business, right? With well, you need to do the place to search. Basically, all you have to do here is say if the length of a list. And then here, if a list place to search, return true. Else if this, let's say, how do we change the function to use slices? This is how we do it. We just change these into slices. Like this. And I think we're good, right? Oh yeah, but we don't have start and end. So length of a list and 0. And so this has to be really just length of a list because we're going to add 0 to it. So this is two ways to write the same thing. Hopefully they work. Let's test them out. Okay. So let's generate a list. So say for I in range, say 100, my list equals something. My list dot append random dot randint, say 0 to 100 or whatever, and then we will say my list what dot sort. In fact, we can even use one of our own sorts, but the inbuilt Python sort will be faster than any of the sorts we implement in Python, mainly because it's running in the underlying C. And then what we do here is now we can binary search. So let's print out the list, my list, and then let's get an element to search. And then finally we'll search the list for X. And then we'll print out if we found it or not. I think another thing that'll help us is that at every step we should just print out like this. We'll just print out all the data from every step. Okay, so let's do this thing. Let's see what happens. So let's look for an element. What element should we look for? We are going to look for, let's look for 30, okay? So in the first go around, remember that this is the start, this is the end, right? This is the element, this is the midpoint, and this is the element that we found there. So the indices start at 0 and go up to 100. We found the midpoint is 50, so that's the minimum. That's the midpoint index, not the actual midpoint. Here's the actual midpoint, and then we say, okay, so 46 we found one of these 46s, and so then we know that 30 has to be somewhere in here less than it. So then we go from 0 to 50, right? Our midpoint value is 25. Our actual midpoint is 23. So one of these is the midpoint. And so now we're considering the list between, what, 46 and 23, so something like this, right? And so our middle element is going to be in the 32, 34, 35 range. And what do we see? 32, I guess? So then it says 26, 50, and then the midpoint is 38, right? Because 25 plus 12.5, which is, one half of that, is equal to 37.5, so I guess it just gets rounded up to 38 because of the plus 1 business. So then we find 32. And so now we're looking between indices 26 and 38. Maybe we'll shrink this list down next time to have only 10 elements. But anyway, so, and then we have 33, 38. The middle index is 35. and we actually find the element there, and we return true. Okay, so let's do this again. So now let's search for, say, 95, and see what happens. Right, so here the middle element is 66, and you see here with 10 elements, right? With 10 elements, it's never going to be the exact middle, because you say, what is the exact middle? Well, there are 1, 2, 3, 4, 5 elements on this side, 1, 2, 3, 4, 5 elements on this side. The exact middle is actually somewhere in between 62 and 66. So the way our algorithm does it, it just kind of rounds up a little bit, but that's not, it's only because we divide the length by 2, and the length is always the max index plus 1, so that's why we end up with 66 and not 62. If you subtract 1 from the length of the list and then divide by 2, then you would end up with 62. The whole point is that it doesn't really matter what you do as long as you're consistent. So anyway, we end up with 66, so there's 5 elements on this side, there's 4 elements on this side, and so now we're looking from indices 6 to 10. And so what are we going to do? We are going to look at index 8. Index 8 is right here, which is 98. And then we're going from index 6 to 8. So here is index 6 up to 8, right? But we're actually not including this index, so it's like 6 and 7, basically. The quote-unquote middle index is the one at 91. Now, you could ask, why isn't it at 75? The answer is, again, the rounding up business, because there's only 2 elements. So we have to pick one of them, and there's not really a middle. If you pick the lower one, you'd be like, well, that's not the middle, and you pick the upper one, that's also not the middle. So we just kind of pick one at random. We just pick the upper one. And then finally, that's not true, so then we end up here, where we're searching 8, 8, index 8, 98, right? The problem with this is that 98 isn't equal to 95, so then our algorithm returns false, and we're done. So this is an example where we did a binary search and we didn't find what we were looking for. Okay. So, all right. So now let's do a little bit of time racing between the two things, right? So let's create a list with, say, 100,000 elements in it. No, that's not 100,000. There we go. That'll create a 100,000 thing. And so now, instead of asking for what the element is that we want to look for, what I want to do is I want to just say for, say, I in range 10. So we're going to run 10 tests. And what we're going to do is we're going to say find me equals random.randint, say 0 to 1,000. And then instead of searching for X, we'll search for find me. And okay. And now what we're going to do is we are going to time the difference between a linear search and a binary search. So we need some time business. So let's go and steal the time stuff out of the timing functions. Where is it? Here we are. That's pretty easy. So binary start, and then we run the thing, and then we say binary time equals time.time minus binary start. There we go. And then again here we'll do linear start, right? Linear start is time.time, and then linear time is equal to time.time minus lin time, or lin start. And so now we'll just print out, in fact, I don't even know that we need to print out the actual results from these. We can just do this. We'll just print out the times. So we'll say, the binary time was blah, the linear time was blah. Something like that. And we'll just run it 10 times. And then maybe we'll even average them, right? So we can say And so what we'll do here is at the end, we'll just say bin average plus equals bin time, nope, and lin average plus equals lin time. And then at the very end, we will say the average times, right? And the linear average time. And so here what we'll do is we'll say divided equals 10, and average divided equals 10. And so here we go, almost done. So divide by the binary average, linear average, and we're good. Okay, so now we can run this test and just see what happens. Okay, that didn't tell us anything. Maybe we need a bigger list. Because if you notice, these are near 0.1 milliseconds, which, if you remember from our last tests, was kind of the accuracy range of the. Let's make it 10 million. Okay. Maybe we should have just made it 1 million. I think constructing it is taking a long time. Hopefully this is 10 million. Okay, it is. Oh, it was trying to print it. Oh, that's why. Okay. So, yeah. Alright, so if we look at this thing, right, what do we see here? We see that we're printing way too much stuff. We need to not print this stuff in the binary search. So printing slows your program down a lot, actually. So, this is a binary time that was kind of disadvantaged by the fact that it was printing while it was going, whereas this wasn't printing anything. So this is more fair. But notice here that we have 1 decimal here, and we have 1, 2, 3 decimals here. So the point is that this is what? It's approximately 500 times, 600 times as fast, or maybe 300, somewhere between 300 and 500 times as fast, right? I guess we could use a calculator to compute the ratio. Yeah, 318 times as fast, on average. And so why, right? Why is the binary search time so much faster? Right, so let's go back to doing some math. So basically the point is, and this is basically how a lot of this stuff works, is we want to count the number of steps that happens in each algorithm. Okay? And so here I'm going to do a little bit of analysis of linear search. So the linear search analysis is basically going to go like this. On average, we go from, so think about it this way. We're going to have to search the entire list, right? But as soon as we find what we're looking for, we can quit. So that's the thing to keep in mind, right? As soon as we find the thing we're looking for, as soon as we find the element, we can exit the loop and return, right? But if we don't find the element, or if the element's towards the end, right? If the element isn't in there, in the list, or we can't, or it's at the end, we have to search almost the entire list, or the entire list, right? And so basically the way I kind of look at this is that you ask, what is the probability that the thing, whatever you're looking for, is in position 0, right? And the probability of that is equal to 1 over the size of the list, assuming that the thing is in the list. And then you say, what is the probability that the thing is in position 1? That's also 1 over n. The probability that the thing is in position 2, also 1 over n. All the way down to the probability that the thing is in the last position, or in position n. And that's also 1 over n. Right, so the probability is all 1 over n's, and so basically the question is how many things do we have to search, right? If the thing is in position 0, then we only have to search one thing. If the thing is in position 2, we only have to search 2 things. If the thing is in position, if it's in position 1, we have to search 2 things. Remember, I guess actually I should do position n-1 like this. All right, so we have to search 3 things all the way up to we have to search n things. Right, and I think we went through this last time where I proved that the sum, right, if you take the sum of from, let's say, k is equal to 0, or really 1 up to n of k, right, and that's equal to 1 plus 2 plus 3 plus dots plus n, or big N, that's equal to this. It's equal to n times n plus 1 divided by 2. So now I just have to wait for it to render. Almost. And there we go. Okay, let's find it now. Here it is. So, okay, so here it is. So basically, and then if you just if you tack on a 1 over n on the front of the thing, that's equivalent to basically dividing the whole thing by n. And if you divide the whole thing by n, then you are going to get the expected number of steps, right? Which is approximately equal to n plus 1 divided by 2, right? That's the average number of expected steps that we're going to get. So this is our analysis for a linear search, right? Our analysis for linear search is that on average, we expect to see, basically, I mean, I'm going to ignore this plus 1. I'm just going to say n over 2 steps to look for the element, right? That's what we're going to see. Okay? All right. Cool. So n over 2 steps, that's the answer for this one. But now you ask, well, okay, that's all the linear search analysis. What about the binary search analysis? So let's do the binary search analysis. And then we'll think about the binary search. So how many things do we have to do for the binary search? So let's go back to the thing that I was saying in the beginning, right? If we have a list of size n, then the next list that we're going to search is of size n over 2. Then we're going to search a list of size n over 4, then n over 8, then n over something is equal to 1. So there's a bunch of stuff that happens in here and then there. So how many times do we have to keep dividing the list in half before we get down to something like this? And so here's my claim, right? What numbers go like 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,384, 32,768, 65,536, etc., right? I mean, what numbers do this? Yeah, binary meaning powers of 2, yeah. So similar, and then, 131, 072. Basically, the point here is that here's some powers of 2, right? And, yeah, a little bit. So, here's the point. Those are powers. If you're a computer science major, you should know these. you should recognize these, right? These are numbers that should never surprise you. Probably, maybe up until about here, right? I don't care about these ones so much, but all of these numbers should be kind of eventually baked into your brains. And the reason is because if you don't see them a million times in computer science, you will. So, anyway. Yeah, so these numbers are kind of, they're very important. They're powers of 2, and you're going to see them a billion times in this major. Yeah, I mean, as long as you know the ones up to 1024, that's fine, especially because 1024 is really 2 to the 10th. So it's a good one to know. So here's the point, right? Here's the point. Eventually, let's do some more latexing. The other reason why I was writing down powers of 2 is because I was giving people a while to think about them. You know, I figured just rattling off numbers would help. That's the pattern. That's the pattern. Yeah, so eventually we're going to get to something like this, right? Where 2 to the k, which is actually equal to the number of steps, is approximately equal to n. Oh, because of the game, what is that game called? 2048, or is it 4096? I forget the one you have to go up to. Yeah, and so here what I'm going to do is I'm going to do something kind of computer science-y. I'm going to take the LG, right, and maybe I'll just do math RM, LG of, what am I doing? 2 to the k is approximately equal to n, and so the good news is that this is equal to k, and k is equal to the number of steps. Well, of course, I mean, there's all kinds of powers of 2. You can't just stop at 2048. So anyway, okay, so here's the thing. The number of steps that we're actually going to do for a binary search is at most, right? This is at most LGN of steps. Now, you might be asking yourself, what the heck is LG of n? And so I'll tell you. So LG of n, so, okay, let's go back a second and, go back to Algebra 2 or pre-calculus. Remember pre-calc, or whatever, where you talked about log, right? Now, what does log do, right? What log does is it asks what power of 10 is x, right? So the log of x asks what power of 10 is x. And so ln, right, of x is asking the same question. It's what power of e is x, and of course e, as you all know, is approximately 2.782818.459. And you might be asking, what the heck about that? And the answer is go to calculus. This is not the place to be talking about e, right? E is beautiful. E is a natural thing, right? It occurs in mathematics based on, there's so many different ways to get E. It just pops out of everything. You have the Euler formula, like E to the I theta is equal to cosine theta plus I sine theta. You have all kinds of beautiful formulas based on E. But we're not doing any of those. What we're talking about is LG of x, which asks what power of 2 is x. And the reason why 2 is important is because, hey, right? I used to be able to. I don't know all the digits of pi. I used to know about 100 digits, but I don't now. The joke is that 3.14 gets you to the moon. So, okay. Anyway, so you know log base 10, you know the natural log, and here's LG, right? What power of 2 is x? And so you may never see LG again, but if you take data structures or algorithms with me, you will definitely see, well, yeah, pi and e are both transcendental, which means they are infinitely long, but they are also irrational, which means they don't repeat. And also, they are not expressible. Well, irrational just means they're not as a rational number, but if they were a rational number, they would repeat in their decimal expansion. It also means they're not a solution of any polynomial equation in rational coefficients. So there is no, you cannot write any equation down like x squared or x to the 10th minus, say, x to the 9th plus x to the 8th or whatever plus ... equals 0 and x equals pi. Won't happen. Okay, so the point is that LG is the log base 2. So that's what I'm doing here, and that's why LG cancels out with the 2, and I just get the number of steps. So basically the point is, what I want to do now is I want to look at the difference in graphs. So let me pull up my little trusty, where is it? Here it is, Desmos. So I want to look at y equals, say, natural log of x. I mean, so it's good enough, you might say, but that's not LG. Yeah, my dog is clicking around on the floor, so she's like jumping around. And so here is the graph of y equals, say, x over 2. Oops, I want x divided by 2. There we go. So here we are. So remember that these are graphs of time, right? The amount of time it takes to do a certain amount of calculation, or really the amount of steps, right? And so the thing is that you always want the number of steps to be smaller. So as you notice, as n, which is x in this case, right, as it gets large, you notice that log kind of starts to flatten out like this. Log still goes to infinity, but it goes to infinity way slower than x over 2. So that's the point here, is that the amount of steps at any point is way lower for the natural log, which, so we could also just do, I think, log of x. I think, would that do log base 2? No, it doesn't like it. We could use the log conversion formula. There we go. That's log base 2. So, all right. So that's the point, is that the number of steps in a binary search is going to be way lower than the number of steps in a linear search, right? And that's the whole idea of asymptotic analysis, is trying to figure out which one's going to do better, not just on 100 elements, but say we took this, let's say we go out to, if the list was long, doing random to do the splits would be faster. It could be faster, it could be slower, right? If you accidentally split towards the end of the list, then it would be worse. If you accidentally split towards the middle, or if you accidentally split towards the answer, it would be better. If you accidentally split towards like the wrong end and then like had to chunk your way in, then it starts to look a bit more linear. The only thing about randomized algorithms is that then you have to talk about like how random the thing is, and you have to do even more probability calculations to know. So you're asking a very complicated question, actually, way beyond. I'm not going to try to do the calculation in real time because I would be terrified. So right, so here's our graph of y is equal to x over 2, and here's our graph of the binary search number of steps, right? So this graph looks vertical, and by the time it gets all the way out to here, right, so we'd have to zoom this out vertically also to approximately, we'd have to zoom this out like this, and then here's what it does to the other function, right? So if we look, so remember what 10 to the 7th is. 10 to the 7th is approximately 10 million. So this is approximately 12 million, right? So when we have 12 million elements, well, I think actually we did have about 10 million elements, so we were around here. So the search time here looks like 0, the search time here looks like 1,000,000, right? So basically here, there's no comparison between the binary search and the linear search, right? Of course you might say, well, sometimes I can't use the binary search because the thing isn't sorted. I agree. Okay, so that's the point here. The point here is that now that we know the two functions, right, the number of steps for a linear search is about n/2, the number of steps for a binary search is about lg of n is the number of steps for a binary search, and n/2 is the number of steps for a linear search. We can say binary searches will be faster, and they will be way, 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 way faster. Okay? A triple search or a trio search where you split the... Yeah, you could do that. You could do that, but then you don't get an LG, you get a log base 3 instead of log base 2. Okay. And so that's not to say, so there are conditions in which a binary search, well, so the thing is you cannot do, so you just can't do a binary search on an unsorted list, right? Because the only assumption that we made when we decided should we go under or over, yeah, you could, but the benefits become less and less. So, like for instance here, if we look at the difference between, okay, I need to do something like this. If I, let's see, y is equal to log base x over log base x, log of x divided by log of 3. So we see here is the comparison between a binary search and what you're suggesting is like a trinary search, right? So a trinary search would be better in the long run than a binary search, but it's not, you notice that it kind of tracks with it. It's not infinitely better, right? It's just kind of a constant coefficient better. And so that's why we usually teach binary search, because, you know, it's the binary search gets the idea of the algorithm across, and it's not quite as complicated as a trinary search would be. So, yep, okay. So now let's think about merge sorts. So let's go back to sorting and think about quick sort, merge sort, maybe the other sorts, right? Basically, I went through why other sorts, the quadratic sorts, we already know that they take about n squared divided by 2 steps. So that's a lot of step. So let's think about, say, merge sort first. I think merge sort analysis is probably the best. Let me go through the merge sort analysis with you. So let's talk about merge sort. 3. Let's make something like this. That's 6. That's 12. Let's paste one more time and get 18. Okay. So let's talk about merge sort. Right? So what does merge sort do? Right? What merge sort does is it takes a list and it doesn't care anything about what's inside of the list. Remember, it just splits the list in half, like this. So one half of the list goes into one of the recursions of merge sort, and the other half goes into the other half, right? And then, of course, these are both size 9, so we have to make a decision. So what I'm going to do, I'm going to split like this. I'm going to say 4 go into here, and 5 go into the top half, right? And then I'm going to do the same thing here. 4 go into here, and 5 go into the top half. And then we have to divide again, right? So this is step 1 of the merge sort, right? If this is step 1, this is step 2. This will be step 3. And then what's step 4? Step 4 is the same business. You divide this one in half, so you get 2 and 2, like this. Here we have to get something like 2 and 3. Unfortunately, odd numbers are always going to screw things up. And then we'll get 2 and 2 again here. And then finally what you're going to do is you're going to get 2 and 3. And then what's the last step, right? The last step is or the second to last step. Unfortunately, there's a step 6, but step 5 is this. Step 5 is what? We divide this in half, so we get 1 and 1, like that, right? And then we're going to have to merge everything back together, right? And so then this is all split up. This one is almost all split up, except this gets split into... Let's just actually say that step 5 breaks everything up, even though it doesn't, you know, and there's going to be a lot of them here, so it doesn't quite do this. There's actually a step 6, but let's ignore that fact just for the sake of like having everything look good. Okay, so now that everything's broken up, right, now we have to merge these things back together, right? So how do we merge back together? Right, we merge back together by saying, okay, take those two things and merge them. So that takes 2 time here, 2 time here, 2 time here, 3 time here, 2, you know, etc. So basically at every step, right, we have to go through every single element in order to merge them back together. So basically every step has n substeps. And the substeps are the merge process, where we go through each divided list and put them back together in order, right? So basically that's the point, is that every step here has n substeps, which is the merge process. Okay, so now the question is not how many substeps are there, but how many total steps are there? And the answer is, it's the same thing as for binary search, right? It's how many times do we need before we can divide a list up into all of its parts. So it's the same analysis as for binary search, which is basically just asking, right? In fact, I'm just going to do this thing again. I'm just going to copy paste it, basically. So the number of steps is equal to k, which is equal to the log of n, right? The lg of n. And so the number of steps is going to be equal to about log of n, and the number of substeps is equal to n for each time we go through this list. So the point is, so the question is how many substeps or, you know, total things do we have to do, right? And the answer is, well, for each one of these log n steps, there are n substeps. So then what we're going to get is, literally what we're going to get is n times, lg of n. And never restart. Restarting is sinful. Here we go. So that's basically what we get. We get n times the log of n. And so for merge sort, that's the expected number of steps that we get. Okay? And so that's a really cool thing, because let's go back and look again at our functions. So let's look at, say, an n squared over 2 sort. So let's say y equals n squared divided, come on, you know what I want to do. That's what I want to do. That's n squared divided by 2, and then here is n times, I'm even just going to do the natural log of n, because I know that these things generally don't know what LG is. So, okay. Interesting, right? Interesting. So the first thing you might notice is that the amount of time here is negative, the number of steps is negative, but you notice that here the number of steps is 0 for an element with an undefined list, or an empty list. Empty list is what I was looking for. And we have 0 time for a list of size 1. Basically what that means is we're just hitting the base case. You notice here that for a list of size 1 it takes what? 0.5. So it's about the same. So this is not a problem. So it's not an extra topic. It's part of our curriculum. But it's something that would show up more on a multiple choice style exam than it would in your coding. That's right. Yes. Okay, so if we look at these two curves, here you can't actually see much of a difference. You see that blue is beating red, but you might think to yourself, like, they're not beating red by that much, so I'm not impressed, right? Why did we bother to do these complicated logarithmic sorts if blue isn't going to beat red by more than this much, right? That's not a lot. Or really, I shouldn't draw it horizontally, I should say vertically. It's not beating it by that much. So, but you got to notice what your x scale is, right? Our x scale here is 2, 4, 6, 8, 10, 12. We don't really care about the number. Like, you can manually, right? I could get a human to sort a list of 10 elements, right? This is not the point of computer science. Nothing down here is the point, right? Computers, the whole point of computers is that we use them to do calculations that we can otherwise do in our, if you just wrote down the numbers and then rewrote them in an ordered fashion, right? So anything under 20 here, none of this is really the point, right? You see that, yeah, it's kind of getting more extreme. Red is losing to blue, and by losing, I mean it's the opposite of growing faster, right? Because this is an analysis of steps or time or something like that. So as red is increasing faster, it's actually going slower because it's doing more steps. The time it takes is increasing, right? So as this function goes up faster, the amount of time is going up faster, which is the problem. So now let's go and blow it out to a large scale. So let's say that we go out to 10,000 maybe, and let's take y up to, say, what is it? Something like that. So now you see the difference, right, between the red algorithm, which is our, insertion sort, selection sort, bubble sort. That's what these are doing here. And here's merge sort, right? Merge sort is operating, you see, it's beating it by so much, right, that you can't even see the red function that's so high, right? So it's a little bit of, what should I say about this? Yeah, I guess I've said what I wanted to say. So the blue function is taking time, right? It's not free to sort elements. But if we look at the scale for the red function, it's gone, right? By the time that the red function gets out to here, it's probably orders of magnitude, it's up so high that it's taken a huge amount of time. And so at least here, this is kind of scaling linearly. And you see how n log n, if you didn't see this equation, you might think that it's almost linear. It's not exactly linear. A linear algorithm will beat it. So this is just n, right? This is n. Here's n log n. So n log n is worse than n, but it's just so much better than n squared, right? And this is what we really concern ourselves with in computer science. And this is the idea here, is what's better, n log n, n squared. The answer is O of n is better. Well, I shouldn't say O, I haven't introduced it. N steps is better, right? But we don't have a sorting algorithm yet that runs in n steps, so we can't do that. So green doesn't matter, so we have to pick either blue or red, so we pick blue. because we want to solve problems in the amount of time that we live. We don't want to solve problems in the amount of time that the universe has existed. So, oh yes, this is a good time to talk about Bobo Sort. So Bobo Sort is a meme, right? And so what kind of meme is it? It's the kind of meme, it's like a joke in computer science, right? But it's a good joke in the sense that it's good for analysis, right? Good to think about. Good for analysis. Don't ever actually do this thing. And so here's what Bobo Sort does. Bobo Sort does this. It says, how many ways, so how many permutations are there of n elements, right? So if we have n elements, I don't know if you've taken enough combinatorics or you've seen this maybe in pre-calculus, how many permutations are there of n elements? And the answer is n factorial. It's the number of, and so what is a permutation? A permutation is a reordering. Okay? So that's all it means. So for instance, if you have the numbers 1, 2, 3, the permutations are 1, 3, 2, 2, 1, 3, 2, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 3, 2, 1. Those are the permutations of 3 elements. Here's the permutations of 4 elements. So get ready. It's this, where you have 1, 2, 3, 4 with 4s at the end. Well, yeah. And then we'll do 1, 3, 4, 2, 1, 2, 4, 3. And then we have more of them, so then we'll do 1, 4, 2, 3, 1, 4, 3, 2. So there are 6 of those, and then let's make some more of these. So we need 2, 1, 4, 3, 2, God, 2, 4, 3, 1, 2, 4, 1, 3, and then there's a 2, 3, 1 that I haven't thought of, 2, 3, 4, 1. Hopefully I haven't written a duplicate down. And so then here, let's do more of them. So we get 3, 1, 4, 2, 3, 2, 4, 1, 3, so 3, 2, 4, 1 should go with 3, 2, 1, 4, something like this, and then 3, 4, 1, 2, 3, 4, 2, 1. I think those are all unique. And then finally, yeah, I mean, I don't know why we've done permutation problems. And then there's all the 4s, and there's 6 of them. And I'm getting lazy here. Actually, you know what? Let's just write a permutation generating algorithm. Here we go. So, and then we'll say used. And then we will just say, okay, let's see, for I in range 1 to n plus 1, let's see, what am I doing here? So for I in range 1 to n plus 1, if I is in used or not in used, then we will say permutation n current plus used plus I. There we go. If length of used is equal to n, then we'll print current and return. I think this might do it. This might do it or it will explode, right? One or the other. So let's run there we go. There we are. Let's see what this does. Here we go. Here's all the permutations, right? And so as it turns out, there are 24 of these. And then if you calculate the permutations on 5, there's going to be, if we counted these, which we shouldn't do by hand, basically what I'm going to do, I'm going to do the trick, the stupid trick. I'm going to cut, and then I'm going to paste it into a document in Notepad++, where you can see that there's 120 lines, which means there's 120 of these things, right? So that's it. And so basically the point is that the number of permutations is equal to n factorial. Now, here's the weird thing, right? If you have a list, so let's get back to Bobo Sort. If you have a list of n elements, there is at least one permutation which is sorted, right? If the elements are all distinct, there is exactly one, but if there's some duplicate elements, then there's a little bit of wiggle room in that. So the point is that if you have a bunch of different elements, right? You have a list of 10 million elements, and it's just numbers from 1 to 10 million, and there's no duplicates. Then there's exactly, if there's no duplicates, then there's exactly one permutation that is sorted. So here's what Bobo Sort does. It says for p in permutations of our list. Okay? So you need a way to generate all the different permutations, but once you do that, you say for each permutation, if the permutation of our list is sorted, then return the permutation on our list. Right? And that's what Bobo Sort does. Right? So the number of steps here, it's actually a little bit worse, but the number of steps, because you might actually have to calculate, a way to generate all the permutations, which isn't free, and then you have to permute all the things in the list, which isn't free, but it takes, some time to do this. But if you think about it, the most time is going to be used up by this, right? 4p and the permutations on our list. So basically what's going to happen is there's going to be some permutation that is sorted, but we have to find which one, right? We have to find which permutation is the correct one to sort the list, right? And so you might be thinking to yourself, well, how many permutations can there be of a list of size n? And the answer is n factorial. Excuse me. So there's n factorial steps for the for loop. And then actually determining if a thing is sorted takes an additional n. So actually it takes n times n factorial steps to solve Bobo Sort. And that's assuming that it doesn't take any time to calculate all the different permutations, which I think you can kind of do in constant time. Well, not really. I think you might need like some amount of time to do that, but it's at least, right? Wikipedia says it's n plus 1 factorial, which is approximately, right? It's approximately n times n factorial. The point is that now I want to look at n factorial, or n times n factorial. Let's look at that on our little graph sheet. So, right, so you might think our quadratic sorts are bad, right? And I've been telling you they're bad. So here's n plus 1 factorial. Okay? So it's this purple line here that you can't almost see. So let's resume. Whoa. Let's not look over there. So if anyone knows what this is doing, then, well, why aren't you in complex analysis? But anyway, let's ignore what it's doing over there for the negatives. Just pay attention to what it's doing here for the positives. So, I mean, it could be, right? So I'm just guesstimating here, right? N squared times n. Why would it be n squared, though? I mean, look, this is... Let's just assume it's about... I mean, these are about the same, right? Wikipedia says this, and I agree, and this is about right. No, don't worry about it. So here's the thing. It doesn't... the argument I'm about to make is that it could be n squared times n factorial. It doesn't matter. It really doesn't matter. And here's why it doesn't matter. Let's zoom out here, right? Oh, God. We have to make sure we don't look at the negatives. The negatives... So if anyone knows what the gamma function is, that's what this thing is doing over here. This is the gamma function. But the point is that you notice that here's the red curve and here's the purple curve. The purple curve is going to get way worse. So let's change our x values from, let's make sure we don't see any negatives. And we say, okay, 0, and let's go up to, say, 2,000. And let's change this from whatever this is to, say, so here's a good example, right? Once we're looking just from 0 to 2,000, here's our red line. So our red line that was performing so terribly before and taking, longer than the number of seconds in the universe to sort whatever, here's the purple line. It's still almost vertical, right? So n plus 1 factorial is basically, this is as bad as it gets, right, in terms of an algorithm. If you ever end up with an algorithm with an n factorial in it, you can generally run it for things under 10, maybe things under 20. If you get up to 50, you will start to see a massive slowdown. And then if you tried to plug in something like n equals 2,000, let's just look at what 2,000 factorial is. I think... let's see, 2,000 factorial. Here it is. So Windows Calculator says it's 3.31 times, the E plus is an engineering notation for times 10 to the power of, right? So this is 3.3 times 10 to the power of 5,735, right? 5,735. That's not 5,700, that's the power that we're raising 10 to, right? So there's 3.3 with 5,734 other digits following behind it, right? So, that's a lot of time, right? Given that the universe has only existed for something on the order of a few billion years, this is factors longer, right? This is, so much longer than the length of the universe that it's kind of inconceivable. So that's the point here. So there are algorithms that can take basic, this is length of the universe. This is like length of the universe squared, or length of the universe time, to the 100th power, right? Before you get to algorithms that run this slow. This stuff is running within our lifetime, right? And n log n runs quickly enough to where you can actually make go with it, right? So the point of this lecture, and of course you might ask, like, what do I really need to know out of this lecture? So let me tell you. Basically, you should know that the log of n is less than n, which is less than n log n, which is less than n squared, which is less than n factorial. And what you should really know is lesser numbers of steps, meaning smaller functions, is, in our heads, in computer science, better performance. Okay? So it might be a little weird because you might be thinking, oh, it's the bigger function that's the better performance. No, the smaller function is the better performance because, remember, we are measuring time. Well, we're measuring steps, right? Really, is what we're measuring. which is, and then of course what we do is we say steps take some constant, there's some factor f which converts from steps into time, right? So there's a factor of like, oh, a computer can do where f is equal to the number of steps per second, and then now we're in the range of time in seconds, right? So that's the idea here, is that it's true that I've only ever talked about steps, and I've not really been talking about time. But there is some kind of conversion factor f that you can say the number of steps that my computer does per second is this, therefore the amount of time that I'm actually taking is this, and so that's why these functions that we're measuring are, we're measuring steps, but it's just a proxy for measuring time. And so here, basically the other thing to know from this lecture is that log n, that's binary search, right? That's the only function you currently know, I think, that takes log n time. I mean, you could invent another function, but I think that's currently the only one we know. Linear search. Then n log n, that's quick sort and merge sort, right? N squared, that's insertion, selection, bubble sort. And then finally, n factorial, silly Bobo sort, right? And so you don't really have to know anything about Bobo sort. It's never going to occur on a test. The whole point about it is just to understand that that when you were doing all those limits, basically in calculus, and you were talking about how functions go off to infinity, right? And you were talking about how functions can behave differently, where if you take a limit of f of x over g of x as x goes to infinity, well, maybe I'll just do it in LaTeX. If you want to look at two functions and you say, what happens as the limit as x goes to infinity of, f of x over g of x, like this, this is where some of that stuff has an application. It has an application because if you look at the limit of the two functions and say the limit goes to, so there's a few different options. So either the thing can be infinity, right? Which means that f performs way slower than g, right? Or it can be some limit, right? So some number, which means that f and g perform similarly, meaning a constant multiple L apart. So one of them is better, but they generally perform about the same. Or it can be 0. Now you might say it could be negative infinity, but if it's negative infinity, then we're not dealing with time. There's only certain functions that we ever plug into these limits. So if it's 0, then what that means is that f performs better, meaning faster, than g. So that means that g goes off to infinity way faster than f. So it's dominated f, and it's pulled it down to 0. So basically, so those are the three possibilities. So basically here, that's the way that this kind of stuff works, is that this is the reason that we actually talk about all this. So next time, what I'm actually going to discuss, so I'm glad I was able to give this whole lecture, and I only accidentally said it once. So next time, we'll talk about big O. Right, so big O is the math formulation of all of this, right? It's kind of the structure, the rigor that makes it all work. Okay, and so that's the point here, is that we'll talk about big O next time. I think I've done an entire lecture where other than the time where I accidentally said it once, I didn't really mention it, and that's good, I think, because when I used to do this lecture and I used to talk about big O, I think it confused just about everybody, and we never really got, there just didn't seem to be a lot of understanding going on. So the point of this is that I believe that this should hopefully tell you more about what we're going to be doing next time. We're going to be taking all the number of step calculations and just kind of analyzing them in a more structured way. Okay, so that's all I really have for this lecture. Yeah. Hope hopefully this made some kind of sense in the end, right? And that's my only hope, is that this made some kind of sense. And so if you understood somewhat, if G is bigger faster, that's worse. Because remember, we are measuring time. A bigger time means a longer time to run, means worse performance, right? So smaller functions are better, bigger functions are worse. I think that if that's the only thing you get out of this lecture today, then you've got it. So, yeah, and we'll talk about more stuff next time. All right. So, all right, I will let everyone go now. Later.